Thank you, and thanks to everyone for coming. So I'm gonna switch a little bit to talk about how we can use computational methods to understand users. By users, I mean buyers and sellers dynamics on strategic platforms that learn from buyers and sellers data.
You might want to click this slide.
I think I'll just use this work is in collaboration with David, Garrett, and Robert, who are students from Rutgers universities. And the general theme is I want to pitch that economics and computation is a good fit for designing platform-mediated economic system, as the modern sellers are increasingly modular and disintermediated, relying on the coordination of the market-driven platform. And all those buyers and sellers interactions are governed through economic mechanisms. And these include the fees, the matching, the pricing, the reputation system set by the platform. And this work is really inspired by our prior work where we studied the platform behavior during market shock. And by market shock, you can understand it as a period, for example, during COVID and during a specific area where people had hard times access the physical stores or like physical restaurant, for example. And during that period, we observed that the platform fee structure and the platform matching policy can really heavily affect the seller diversity and viability on the platform. And the main theme is to ask, how can we combine computational methods, specifically multi-agent simulation and reinforcement learning and game theoretic analysis, to understand the impact of different mechanisms on the systematic behavior in regard to the whole platform and economy's efficiency, diversity, and sustainability. And specifically, we want to characterize the dynamics in this interplay among both buyers, sellers, and the platform. So the motivation of the work is that recently we observe a lot of platforms entry into the product space. And some examples include the Amazon Basics product that we see a lot on the Amazon platform. And after the pandemic, this DoorDash actually introduced its own kitchen called DoorDash Kitchen to sell food. And this also applied to mobile platforms. For example, in Apple Store, there are apps developed by Apple instead of third-party developers. And there are questions in regard to what are the real motivation for these platform entry. Are these for value capture? Are these for push sellers for innovation? Or are these for really price and quality control? And on the positive side, those entries can encourage spillover effects on third-party sellers, but there are also some negative aspects with the potential discouragement of innovation, which affect the product diversity, and it will also increase the monopoly power of the platform. And there are also several high-profile cases with the EU finding Google for favoring their own price comparison app over third-party price comparison app, as well as the recent Amazon fine of violating the general data protection regulation, basically using the seller and buyer's personal data to inform their recommendation algorithm. And then people find that on Amazon, they actually scoop up data from its own sellers to inform what kind of product to launch. And the question we would like to ask is, how can we understand the effects of platform entry as informed by marketplace data on those third-party sellers, as well as the efficiency and the diversity of the ecosystem? So at the very beginning, we conduct this empirical evidence, and we would like to get real Amazon data from this platform called Keepa, which tracks different product features and information. And those features include what category the product belongs to, which manufacture, whether it's from it's produced by Amazon or it's produced by third-party sellers. And there are other features like the price, the reviews and ratings, whether it's fulfilled by Amazon, etc. And here we can use the sales rank as a proxy of the demand on Amazon platform. Actually, I believe it's actually calculated by some logarithmic of the demand, and then they rank it. And first of all, I want to show we can use this Keepa data to characterize the pattern of Amazon entry into product space. And we would like to understand how Amazon's entry can affect other third-party sellers. So this shows how Keepa is organizing its database. Basically, we can see whether product is manufactured by Amazon and which category it belongs to. And we can see the sales rank change and price change throughout the period where the product is offered. And so to understand which product category is the most popular for Amazon to enter, we use this distilled BERT to construct a product latent space. Basically, I want to show this. I want to show this interactive map where we can actually see under each category how many Amazon products are there. For example, we can see that if we disable some category, we can see that Amazon offers relatively few products related in the category of automotive, and each dot here represents a subcategory within the root category. And we also observe so it's actually the latent vectors that the distilled BERT recovers. So you can understand it as more as like when you do a really high dimensional PCA and we want to project it on 2 dimensions because for visualization purpose. And here you can see for most root category, they cluster together, showing that it actually makes sense in natural language processing aspect. So you can see the auto, they cluster together. And for sport and outdoors, they cluster relatively together. And we see like the grocery and home and kitchen, they're close to each other. So it's more like, we can definitely interpret like the dimensions, but since it's on the 2-dimensional space, it's a little bit hard, but it's some linear combination of the features. And yeah, so we can see there are relatively few Amazon entered products in art, crafts, and sewing, and relatively few in automotive, but many products in, for example, home and kitchen, as well as office products. So I just want to give an like intuition in general about the current status of how many categories Amazon has already entered. And overall, Amazon has entered 4,000, around 4,000 subcategories out of 20,000 overall categories. And in those categories, we exclude digital products. So you will not see like products related to Alexa and digital books, for example. And here's a showing the fraction of Amazon products in a root category. So the most popular category is clothing, shoes, and jewelry, and then sports and outdoors. And some of the less popular categories are arts, crafts, handmade products, collectibles, and fine art. And apparently this requires a lot of like personal taste, expertise, and innovative cost. And then here's the timeline, just to give an overall sense. So it starts from with clothing, shoes, jewelry, home and kitchen, and recently it enters into industrial and scientific, arts, crafts, and I believe the last one is toys and games.
What would be industrial and scientific versus electronics? What sort of things are in industrial and scientific?
That's a great question. I think for electronics, that's more like, it includes like a lot of accessories and actually, that's a good question. We can go back to the map. And for example, like Monopod has.
Right.
And for the industrial scientific.
I see it's really
Yeah.
so
Pushing and pushing bearings. Yes, so here provides a timeline, and one may wonder why Amazon enter certain categories earlier or but not enter other categories. And here we use a multi-agent computational model trying to model this problem. So we consider seller agent explores a certain product latent space by launching a product at some unexplored place, a space with a one-time cost. So here we assume we do not know what would be the demand or what would be the reward unless you invest and enter it. And after the seller entered the space, both the platform and the seller agents will observe the reward or the demand of the newly launched product space. And the platform will then decide whether and how to exploit the third-party sellers by launching its own product in that product space. Specifically, we model this as a stackable game where the platform is the leader. It can commit to a certain entry policy. And here we consider two popular parameters. The first one is entry time, meaning enter a product space T time steps after it's launched by the seller. So it can reflect some of the patent protection time period where the platform will need to wait until enter the product space. And then we also consider some reward split, which reflect the fraction of reward can be taken by the platform. So it can reflecting the referral fees set by the platform, or even after the platform enters certain space, whether the platform is really doing self-preferencing, giving advantage to its own product. So it's more like we model it as straightforward, a fraction of reward. And sellers as the followers decide to strategically respond with the optimal policy to the costly search problem defined by the platform policy. So the work is kind of related to several economic model and analysis where people derive the equilibrium in the two agent model where there's one platform and one seller. And it's also related to a stackable game for the platform design, where people have studied how to mitigate price collusion and and platform strategic behavior under market shock. And I would like to note that this is also related to the contract design problem, where we can actually consider the platform as a principal and all the third-party sellers as the agents working for that principal, in the sense that the platform is the platform is relying on the sellers to discover what are the reward. So I will briefly run through the model. So basically, if it's a single seller problem, we model as that optimal search induced by the platform parameters. So there's a one-time innovation cost to launch a product, and we have a probabilistic model of reward of each undeveloped product. So the product can either end in good state or bad state. And for each seller, we assume there's a constraint of only selling one product at a time step. And the seller will play optimal search strategy in response to the platform policy. And then for the platform, we assume there's no selling constraint. Basically, the platform can sell multiple items at the same time. And it will choose the TP and alpha that maximize the expected reward. And then a very intuitive solution to solve this optimal sequential search problem is to use the Giddens index, which is defined as the maximum ratio under the optimal stopping time of the expected reward divided by the expected time discount. Basically, intuitively, you can understand it as the constant reward such that one is indifferent between receiving that infinite stream of constant reward and pulling the arm or pulling the arm under the optimal stopping time. And we show that in our case, we can actually calculate Giddens index in a closed form as a function of the platform parameters. And here shows a simple illustrative example where we consider two products. One is safe with 50% chance going to the good state, 50% chance going to the bad state. Another more risky arm with 20% chance where you're going to have a very high reward and 80% of the time you get nothing. So it's very risky. And in this case, we can derive the closed form Giddens index as a function of TP, where TP means when the platform enter. So here we really see 4 different regimes that we can see the seller's exploration strategy is really dependent on this T. So at the very beginning, if the platform sets the T to very small, then the seller will not explore anymore. So it will stick to the safe arm. Versus if we gradually increase this platform entry time, we will see different exploratory behavior. Like in regime 2, it will start with the safe product. And then if it turns out to be in the good state, it will explore the risky one as well. And in the last regime, we see it is exactly the same as an environment without platform entry. So the seller will explore the risky product, and if it's in good state, stick to the good product, stick to the risky product. And then if in the bad state, the seller will switch to the safe product. And we can see similar effect when we increase the platform referral fee. Basically, if the referral is very high, then the seller don't have the incentive to explore. So this is only a single seller problem, but how can we generalize to multiple seller problem? So the difficulty comes from that in our case, the reward will be dependent on the choice of other sellers. So if there are multiple sellers selling the same product or in the same product category, then the reward will be as a function of the good reward as well as the number of sellers in that category. And the transition probability will become unknown as well because it will depend on how many agents will choose to develop product in that category. And here we demonstrate the potential of using a deep Q network to learn the optimal search policy. And we actually show there's a variant of the Q value where we can use to approximate the Giddens index online. So here we can no longer calculate the Giddens index because we do not know the transition probability. So we cannot calculate the Giddens index. But we can show at every stage, either we can continue from that state or we can restart. So with that variant of Q value, we can actually approximate the Giddens index online. And here shows the expected revenue of the platform entry as a function of platform entry time and as a function of platform referral, where the green dots are actually the expected the revenue where the sellers are using the deep Q network to learn the search policy. And here what we can really see is if the platform is forward-looking enough, it will actually not choose to enter the market very early. So remember at the very beginning, we saw the 4 different regimes. Actually, the platform will always choose the earliest T that makes it enter to a certain regime. So here we see that indeed in regime 3, for the first TP that makes the platform to enter the regime 3, it will make the platform to have the highest expected revenue. So here the trade-off is really to whether I want to wait more to encourage the sellers in the environment to explore more so that I can end up entering more a product at good state versus I should exploit at the very beginning and take the users, take the sellers revenue. Yeah, so that's pretty much it. And there are several ways where we can add more strategic aspect to the seller, like how the seller can manipulate the reward via some price adjustment, and how we can combine the data from Keepa actually to calibrate the demand or the reward of the sellers. Yeah, that's pretty much it.